Nice. Wonderful. So these are the data structures for the banker's algorithm. As I already mentioned in last lecture, N denotes the number of processes, M denotes the number of resource types. Then these are the data structures. So let us start with first one, the available. Okay, so available is vector of length m. That means it is associated with resource type. So the entry available of j is equal to k. This denotes that there are k instances of resource type are j available. Remember, even though just j mentioned there, meaning of that is resource type j or j, right? So whenever you come across I, always remember that is pi. Whenever there is j, it is rj. Okay. So meaning of this is, in very simple words, how many instances of each resource type are currently available. That is what the available is. And because we have m resource types, the length of this vector is m. Okay. Next data structure is max. It is the matrix n by m. So number of rows denotes, say for example, number of processes, and columns denotes resource type, so maximum number of instances required for that resource type. So when max of ij is equal to k, meaning of this is process pi needs maximum of k instances for rj. That is what its meaning is. Similarly, allocation is again n by m matrix. Like max denotes maximum number of instances required, allocation denotes what are the currently allocated instances. Okay. So currently, say for example, allocation of ij is equal to k means process pi is currently allocated with k instances of resource rj. That is its meaning, right? Similarly, need. Now given max and allocation, we can simply calculate need. Remember, need is how many resources are still required by that process. So we have maximum requirement, we have current allocation. So maximum requirement minus current allocation is equal to what I need. So the resources that are still required to complete the task at given instance of time, right? So if need of ij is equal to k, this denotes that process pi may need k more instances of resource rj. That is, these are the data structures. Now the banker's algorithm is actually divided into two. One is the safety algorithm and one is resource allocation algorithm. So let us first upon finish this safety algorithm. Okay, the safety algorithm is used to check whether the system is in safe state or not. Can we find some sort of safety sequence? That is the purpose of this safety algorithm. Now for this algorithm, two tentatives, see previous four are definitely required. Those are the available vector, then max, allocation and need matrix. In addition to this, there is something called as a work and finish. Both are the vectors, not matrices, work and finish. And work's length is m and finish's length is n. Meaning of that is m is associated, that is work is associated with the resource types and finish is associated with the processes. Okay. Now, very first step is we need to initialize it. Work is equal to available. So whatever the available resources are there, state of that will be copied to work. Okay, because we know that available is a vector with length m, which denotes what is the current availability of resources. That will be simply copied to work. Remember, even though they are vectors, a single statement is used to denote this in algorithm, because if you are making use of some sort of C-like programming language, you cannot do this. We cannot copy array in this fashion, because anyways we are going to write program for this. Okay, so meaning of this is the array available will be copied into work. So work is assigned with available. And finish of I is equal to false for I equal to 0 to n minus 1. Or if it starts with 1, it is 1 to n. Now meaning of that is we just want to mark how many processes have finished, and initially not a single process is finished. So out of n, all has some task to do. So we'll denote this fact by setting finish of I is equal to false. So work and finish, you can think of these as the temporary vectors used in this algorithm. Okay. Now the step number 2, which is important, find an I such that. Now whenever I say just I, always remember we need to find out a process, Pi. Okay. So find an I such that both the conditions are true. For example, finish of I equal to false. Remember, we have initialized everything to false, right? So finish of I equal to false means this process had some work yet to complete, or in other words, process is not completed. When finish of I is equal to true means that process is finished. Whatever the task is assigned to it is completed. Okay. So we need to find such a process who is not yet finished. That is the condition A. And condition B is need of I is less than equal to work. Now need I is what? Need I is, which we have calculated, max minus, if you go back to previous slide, see here, it is max minus allocation. Now here need of ij, max of ij, allocation of ij is mentioned there, but because we don't want to repeat it for all the processes, it is for a specific ith process, it is just mentioned as need of I. Okay, that is just a notation. So need of I, that means the required resources by process Pi is less than equal to work. And what is work? Work, we have initialized it with available resources. That means if process needs resources that are available, that is the B, and it is not yet finished, that is condition number A. If both are true, then we'll move to step number 3. And if no such I exists, that means maybe first condition is never true. That means all processes have done. Or second is never true. That means deadlock. Simply, a system is not in safe state. So if no such I exists, go to step 4. And in step 4, we are checking if all of the processes have done by checking with if finish of I equals true for all I. If it is true for all I, then system is in safe state. Otherwise, system is not in safe state. So we call that as an unsafe state. Okay. Now, assuming both the conditions are true, let us move to the step number 3. Work is equal to work plus allocation of I. Meaning of that is we found such a process who is not yet finished and whose requirement of resources is less than and equal to available resources. Then what we are doing in step number 3 is work is equal to work plus allocation of I. So that means we have selected that process, we have allocated the resources, and process has finished, and process has released the resources, and these released resources, that means whatever the allocation of I, the resources allocated to process PI will be now added to work, and work we know that it is temporary variable for available. That means available resources will be increased by number of quantity what? Allocation of I, assuming that that process has finished, and finish of I is equal to true. That means we'll mark that process has finished its task. Again, we are going to step number 2. So if we found such a process, we'll consider like that process is finished by setting finish of I equal to true, assuming that all the resources allocated that process will be released. We'll update the vector work and we'll go to step 2. That means now we'll see, say for example, if 5 processes are there, if I found say second process, then we'll look for again first, second, third, fourth, fifth. Now third is say for example, or second is already finished, so we'll just look for 1, 2, 3, 4. If number starts with 0, 0, 1, and then 3, 4. Say for example, second is finished. This is the safety algorithm. Any doubt in this? Now, without making use of these technical notations, if we want to explain the same algorithm, then it will be like this. The available resources will be copied to work, and we'll mark that not a single process is finished by setting finish of I equal to false for all the processes. Then we'll find such a process who is not yet finished. I'm talking about step number 2. We'll find such a process who is not yet finished and whose resource requirement is less than available resources. We'll select such a process, we'll execute it, that process will be marked as finished, the resources allocated to that process will be released and added to the available resources. Again, we'll go back to the step 2, same thing. Find a process who is not yet finished and whose resource requirement is less than available resources. So this loop will be repeated. Now we'll come out of this loop, either A condition is false or B condition is false. That means all processes have done. If that is the case, for coming out of the loop, system is in safe state. And if it is false for say need of I is less than equal to available. So there is not a single process whose demand for resources is greater or less than available resources. Or all the processes requirements are greater than available resources. In that case, we can say system is in unsafe state. So this is the safety algorithm. Is there any doubt in this? So total 6 data structures we use, right? There is something called as available, then max, then the allocation, then the need, and 2 temporary are there actually. One is work and one is finish. Any doubt in this? So this is banker's safety algorithm. Let us move to the next part of this and then we'll go with some example. This is the resource request algorithm for process. any process PI. Okay, resource request algorithm. Now this algorithm will decide whether we have to grant the request by the process or not. Okay. Now request of I, it will denote the request vector for process PI. Again remember, we have mentioned this part in very first thing also. Here, whatever the need is there, it is for all the processes. If you take one slice of that, one row of that, you can treat like that as request of I. Okay, so this is a request vector. That is what is needed by the process. Fine. So if request of ij is equal to k, meaning of that is process Pi wants k instances of resource rj. Okay, so condition number 1. This is the condition number 1, where we want to check request of I is less than equal to need of I. Request of I is less than equal to need of I. Meaning of that is whether the request vector for process I is less than or equal to need, which we have calculated like max minus allocation. Now, if this condition is true, go to step 2. Otherwise, raise the error condition since process has exceeded its maximum claim. Why it is so? Because it is very simple thing. We have calculated need by looking at max minus allocation. Okay, so whatever this request, if it is greater than need, that means it is claiming more than what he has mentioned in the max. Condition number 2 is if request of I is less than equal to available. This is the second condition. Now whatever is requested by process, fine, it is less than what it has claimed, that is okay from the condition number 1. Condition number 2, whatever is the request, if that is less than available, that means we can complete the request because those many resources are available. Then we'll go to step 3. Otherwise, this process has to wait. This process has to wait for others because demand of this process is greater than whatever the available resources are there. Now assuming this again condition true. So if first condition is true, we are going to second step. If second condition is true, we'll go to third. Here we'll pretend that we have allocated the resources to process Pi because requested resources are less than available resources. So we'll simply pretend like we have allocated the resources, and because we have allocated, if you see it here, available will be reduced because available is what? How many resources are available. Now if I say request is granted, that means whatever the requested resources are there, they must be reduced from available. So available becomes available minus request of I. Next thing, allocation of that process has to increase. So we have taken from the operating system whatever the resources. So available resources are reduced and they are added to allocated resources of Pi. So allocation of I is equal to allocation of I plus request of I. So here we have reduced, here we have allocated to the process. And whatever the demand, additional demand, so that is the need actually, need of that process Pi, that has to be subtracted. That has to be subtracted. So it is talking in very simple terms. Say for example, the maximum thing I required is, say for example, 100. Even you can think in terms of money also. So what I need maximum is 100. Currently what is allocated to me is, say for example, 40. So definitely what is need? Need is 60. And what are available? Say available is 75. Say for example, available is 75. So what should happen? If you want to allocate 60, available becomes 75 minus 60. So it becomes 15, right? Allocation, yes, previously it was 40. Now 60 will be added. So allocation becomes 100, something like this. And now what is need? Previously my need was 60. So 60 minus right now allocated is 60 is 0. That means I don't need anything. Okay. So that is how it works. Now after allocating this, we'll invoke the previous algorithm. That is the safety algorithm. And if that algorithm says the resources, the state is safe, the resources are allocated to Pi. Here it is just we are pretending. Okay, we are just modifying data structure. Actual, they are not allocated. The resources will be allocated to Pi if it results in safe state. Okay, and if this allocation results in unsafe state, Pi must wait. Pi must wait, and old resource allocation state is restored. Means what? Whatever the calculations we did here, available equal to available minus request, they will be simply rolled back. That's it. They will be simply. So that is how this resource request algorithm works. Any doubt in this? Of course, we'll see one example on this. Then you'll come to know more clearly. So let us move to the example for banker's algorithm. So here we'll assume there are P processes, P0. So remember it started with 0. So last number is 4. That means here value of n is equal to, what is the value of n? It is equal to 5. There are 3 resource types denoted by A, B and C. So here value of m is equal to 3. Right? And number of instances are also given there. A has maximum 10 instances, B 5 instances, and resource C 7 instances are there. 3 resource types A, B, C. A has got maximum, I'm saying 10 instances, B has got 5 instances, and C has got 7 instances. Now at any given time T0, suppose this is the state. This is the state. Now how to read it, that is important. Let us start with available. 3 resources of type A are available, 3 resources of type B are available, and 2 resources of type C is available. So that is what current. The meaning of that is this is not the initial state of the system. This is the state of system at some time T0. That means A has got total 10, but available are just 3. That means A is allocated somewhere. A is allocated somewhere. And in order to check that, you can do very simple thing. In the allocation, you simply do the addition of this column. So 2 plus 3 plus 2. It gives me 7. Right? So 7 are allocated, 3 are available, total is 10. Now look for second B. 1, 2. 2 resources are allocated. Which resource? Resource type B. So one is allocated to P0 and one is allocated to P3. So 2. 2 are allocated, 3 are available here. 3 are available. 3 plus 2, this gives me 5, total 5. Similarly, resource type C, allocation is 2 plus 1 plus 2. So process P2 is assigned with 2 instances, P4 with 2 instances, and P3 with 1 instance. So total is 5. 5 plus 2 are available, total is 7. Is that okay? Please post it on chat. Is that okay? Okay, fine. So now we have done some simple calculation there, wherein number of resources we mention, how many instances of that resource we mention, then allocation we see here, and then availability is also there. So this is one of the data structure available. I mentioned this is vector of size m. See size m, 1, 2, and 3. So m is equal to 3. Okay. Whereas allocation, this denotes the current allocation of resources to the processes, where each row denotes one process. So you think of this as n by m matrix, where n, that is number of processes, are 5, and I don't think I can draw a small line here. Yes, this is something like this. Now imagine this as a matrix, right? So P0, how to read this is very simple. For a process P0, currently allocation is 0 for resource type A, 1 for resource type B, and 0 for resource type C. Okay. Same is the case for P1, P2, P3, P4. So for P1, resource A, 2 instances have been allocated, B and C nothing. For process 2, 3 instances of resource type A and 2 instances of resource type C are allocated. For P3, resource A, 2 instances, resource B, 1 instance, resource C, 1 instance. Okay. And then, if you see here at the max, see this max is also n by m matrix, where each row denotes the process and each column denotes the resources. Now how to read this is again important. So first row is related with P0. So process P0 needs maximum 7 instances of A, 5 instances of B, and 3 instances of C. Getting it, no? So now given max and allocation, we can simply calculate need matrix of P0. How? The need here, for example, if I want to write the need matrix, maybe it is calculated on next slide also, but it's very simple thing, 7 minus 0. So 7 instances of A is required. So for P0, 7 instances of A is required. For B, maximum need is 5. Current allocation is 1. 5 minus 1 gives me 4. So 4 instances of B is required. And for resource C, 3 is my maximum need, requirement. Current allocation is 0. So 3 minus 0 gives me 3. So this way you can calculate the need matrix. So whatever the 4 data structures I mentioned, they can be calculated like this. So the current allocation, maximum need, or rather maximum requirement for resources, available resources, and the need matrix. They will be simply calculated. See how this need matrix is calculated. The content for matrix need is defined. It is simple thing, max minus allocation. Now if we apply the safe algorithm, whether the system is in safe or not, okay, the system is in safe state since the sequence P1, P3, P4, P2 and P0 satisfy the safety criteria. Now how it satisfies is very simple thing. Again, if we go back to the algorithm, find given these data structures, find the process such that, for example, let me write the available matrix here. Available is 3, 3, 2. So let me write it here. What is 3, 3 and 2? This will be copied to work. Now we'll start with process P0. Need is 743 and available is 332. No, we cannot allocate because 7 units of A are required, but we just have a 3. So we cannot allocate it. So this is not true. Let me cross it. Okay. Now look for P1. Need of P1 is 122 and this is 332. Definitely this can be executed first because need of process P1 is less than whatever the work matrix is there. Now once P1 is finished, this will release 122. That will be updated here. So 3 plus 1, this gives me 4. 3 plus 2 gives me 5 for resource B, and 2 plus 2 gives me 4. Now this is finished. P1 is finished. So finish of P1 is true, something like that. Now 600, no, we cannot right now give it. Reason is requirement for resource A is 6 and available is just 4. Okay. 011, yes, we can give this. 011 4. Janvi said mute yourself. Janvi said mute yourself. Okay. So P3 can be satisfied because requirement is 011. Availability is 454. So this will be done. And these resources will be added again. So 011, this becomes 4 as it is. This becomes 6. And next one becomes 4 plus 1, 5. So this is current state of availability. Now P4, 431, 465. Yes, this can be also allocated. So P4 will be finished. Once P4 is finished, what happens is 4 plus 4, 8 resources, 6 plus 3, 9 resources, and then 5 plus 1, 6 resources. So these are the available resources now, 8, 9, 6. Right? Now, again going back, we can check it. P0 can be also satisfied, 7, 4, 3, and P2 can also be satisfied. So P2 and P0 or P0 and P2, both way. So this will be also done. Resources will be released. This will be also done. Resources will be released. Now all the processes have finished. So finish of I is equal to true for all I. For all processes, they can finish their work. That means system is in safe state, and this is called as safe sequence. This is called as safe sequence. Is that okay? Any doubt in this? Any doubt in this? The same thing is mentioned here. Now I just solve the same thing. Now, if you want to see the complete example, it is available on Moodle. Let me play that because it is just 2 or 3 minutes, I guess. So what I'll do is, let me go back to Moodle and I'll log in there. Those resources I just added in the morning. So I'll go to the operating systems. Let me share first upon the screen for you. Share the Brave browser, right? And this is the algorithm. Can you see this first of all? Because I just maximized it. Yes, fine. Let me play it now. See, this is one of the data structure, as I already mentioned, max. Max is the data structure, which is two-dimensional array of size n by m. Here, 3 resource types A, B, C, and 3 processes P0, P1, P2. Okay. Maximum requirement by P0 is 7, 5, 3. This is the allocation. This is the current allocation of resources A, B, C for processes P0, P1, P2. Need matrix will be simply calculated by doing subtraction. So 7, 5, 3 minus 0, 1, 0 for process 1, 2, and third process. So that is how need is calculated. Total allocations. So they are 5, 1, 2. Now available is 5, 4, 5. Now safety algorithm. First of all, will initialize finish of I equal to false. And work array, we simply copy the available resources there. Now, the steps of algorithm will start. Number of processes are the same example we'll consider. This is the available array that is simply copied to work array, and finish array will be false. That is initialization. Need is less, that will be added to subsequence. Finish of that is true. Work will be updated. Next process, finish of 2, false. Need is less than availability, so that will be kept in subsequence. work will be updated. Finish of 0 is false, need is less, so that both the conditions satisfied. So now all are true. So that is the safety sequence. Now this is resource allocation algorithm. First of all, we need to check two conditions. If requests are less than need, move to step 2. If it is less than available, move to step 3. Now available equal to available minus request 1. Allocation of that process is updated and need is also again we need to execute the safety algorithm. If the system is in safe state, we can assign it. So fine. The same algorithm is the video is uploaded on Moodle. So we'll stop here today.